Okay, welcome. And now we're going to talk about scheduling. An event planner has to juggle many workers completing different tasks, some of which must be completed before others can begin. For example, the banquet tables would need to be arranged in the room before the catering staff could begin setting out silverware. The event planner has to carefully schedule things so that everything gets done in a reasonable amount of time. The problem of scheduling is fairly universal. Contractors need to schedule workers and subcontractors to build a house as quickly as possible. A magazine needs to schedule writers, editors, photographers, typesetters, and others so that an issue can be completed on time. Okay. In this section, we're going to get started in uh, as far as scheduling, get started with the basics. Okay. So to begin thinking about scheduling, let us consider an auto shop that is converting a car from gas to electric. I don't know why they would do that, but hey, let's go with it. A number of steps are involved. A time estimate for each task is given as follows. Task 1, remove engine and gas parts, 2 days. Task 2, steam steam clean the inside of the car, half a day. Task 3, buy an electric motor and speed controller, 2 days for travel. Okay. Task 4, construct the part that connects the motor to the car's transmission, 1 day. Task 5, construct battery racks, 2 days. Task 6, install the motor, half a day. Task 7, install the speed controller, another half day. Task 8, install the battery racks, half a day. And task 9, wire the electricity, a day. Some tasks have to be completed before others can start. We certainly can't install the new motor before removing the old engine, right? There are some tasks, however, that can be worked on simultaneously by 2 different people, like constructing the battery racks and installing the motor. Okay, so those are the types of things we're going to consider. Now, as far as introducing symbolism and how we would write this, let's introduce what a digraph is. Okay, so we're going to create a digraph. A digraph, by definition, is a graphical representation of a set of tasks in which tasks are represented with dots or circles called vertices, and the arrows between the vertices are used to determine the order, right? So, for example, if we look at the diagram below, we have, oops, hold on. So we have this here. So notice that task 1, which is denoted T sub 1, has to be done before task 2, which is denoted T sub 2. Okay? So task 1 and task 2. And then the numbers in parentheses that follow the tasks is the amount of time that it takes to complete that task. Okay? So if we look at all of these parts, these steps 1 through 9 for converting a engine from gasoline to electric, we can look at this digraph in example 1. So we have the start time, right? That's 0. Okay? And then we have tasks that can be done together, right? So for example, if we look at task 1, 3, 4, and 5, right? 1, 3, 4, and 5. Okay, we can remove the engine, buy an electric motor, construct the part that connects the motor to the car's transmission, and construct battery racks. All of those can be done at the same time. They're going to take up different amounts of time to do that, right? So they're going to finish in different times, but they can all be started at the same time. So tasks 1, 3, 4, and 5 are all done here. Okay, now, once task 1 is done, task 2 can be completed. And then once task 3 and 2 can be done. So again, task 3 has to be done before task 6 and 7 can be done, right? But task 2 also needs to be done before tasks 6, 7, and 8 can be done. So there's a connection here. So this digraph allows us to be able to figure out how long and in what order we have to take the tasks, okay? So the time it takes to complete the job will partially depend on how many people are also working on the project. Okay, if we have one person working on the project, obviously that's going to take a lot longer than if we have 4 people working on the project. Okay, now let's look at some definitions. Processors. Okay, in scheduling jargon, the workers completing the task are called processors. While in the example, the processors are humans, in some situations, the processors could be computers, robots, or other machines. For simplicity, we are going to make the very big assumptions that every processor can do every task. So we're assuming cross-training, okay? That they all would take the amount of time to complete, so they all work with the same efficiency, and that only one processor can work on a task at a time. So those are huge assumptions. Maybe not realistic, probably aren't realistic, but for simplicity, that's the assumptions that we're going to make. Finishing time. So the finishing time is how long it takes to complete all the tasks. So the finishing time will depend upon the number of processors and the specific schedule that we come up with. Okay. If we had only one processor working on this task, it is easy to determine the finishing time. Just add up all the individual times for all the different tasks. We assume one person can't work on 2 tasks at the same time, ignoring things like drying times, during which someone could work on another task while another thing, something else is going on, like drying times. Scheduling with one processor, a possible schedule would look like this, with a finishing time of 10 days. Okay? So if only one person was working on this conversion of a gasoline car to an electric car, it would take 10 days to complete. Now, in this schedule, all of the ordering requirements are met. This is certainly not the only possible schedule for one processor, but no other schedule could complete the job in less time. Now, because of this, this is an optimal schedule with optimal finishing time. There is nothing better. Okay, so optimal schedule, the definition of an optimal schedule is the schedule with the shortest possible finishing time. Now, what if we have 2 processors? So for 2 processors, things become more interesting. For small digraphs like this, we probably could fiddle around and guess and check a pretty good schedule. Here would be a possibility, right? So here's one possibility using this schedule here. Okay, so we have 2 processors. One would start number 1, and the other processor would start task 5. So task 1 and task 5. And then once task 3 or task 1 is done, processor 1 can start on task 3. So after 2 days, task 3, because task 5, so if we look at here, so task 1 and 3, or excuse me, task 1 and 5 both take 2 hours, and they here, right? Okay. And so once task 1 and 5 are done, the processors can move to tasks 3 and 4. Okay. Task 3 takes 4 days. Wait, hold on a second. Oh no, 2 hours, right? So that would take it to hour 4, not days, 2 hours. So that would take it to task 4, where task 6, task 4 only takes 1 hour. Okay, and then while processor 2 is done with 4, that can lead to task 2 and 8, which take a half a day. And then when processor 1 starts task 6, processor 2 will be starting task 7, and so on and so forth. So to finish the job, it would take 5.5 days. I'm sorry, I keep saying hours. These are days. So 5.5 days, it would complete the task. Okay. Now, what was processor 2 doing during the last day, right? So right here, the last day, what was processor 2 doing? Well, he was doing nothing. This is called idle time. Okay? Idle time is time in the schedule when there are no tasks available for the processor to work on. So they sit idle. Okay, now, this processor could have been working on another job. Who knows? Okay. Now, is this schedule optimal? Could it have been completed in 5 days? Because every other task had to be completed before task 9, right? Can't do task 9 unless all the other tasks are done. There would be no way that both processors could be busy during task 9. So it is not possible to create a shorter schedule in this example. So how long did it take, or excuse me, how long will it take if we used 3 processors? It would take about 3.33 days. Again, we will guess and check a schedule. Okay, so let's look at a schedule. Here we go. So here we could start tasks 1, 3, and 4 at the same time. So let's look at the diagram again. So 1, 3, and 4. So we could start 1, 3, and 4 at the same time. Okay, why would we do these two? Well, because all 3 of these tasks have to be done in order for task 6 to be done. Well, I mean, they have to be done in order to be able to get to there. Okay, so 3 and 4 have to be done absolutely before 6. But then task 2, after task 1, task 2 has to be done. So task 1 and 2 will take a day and a half. Task 3 and 4 will take 2 and 1 days respectively. So the soonest that we can get task 6 going is 2.5 days. So now that's going to be in the schedule. So let's look at the schedule again. Okay, notice how this is done, right? So now notice how task 1 and 3 take 2 days, right? And then task 4 takes 1 day, but then after task 1 is done, he starts in task 5. Okay, so task 5 right, which also takes 2 days. So task 1 and 3 will get done. Task 4 will get done a day early. Right here. So then task 5 will take 2 days, right? And then after task 1 is done, task 2 begins. And then task 2 leads to task 6. And tasks 6 and 7 get done. Notice that there's idle time here. Okay, because task 7 can't get done, right? Task 7 can't get started until task 2 is complete. So there's some idle time right there. a half a day. And then once tasks 6 and 7 are completed, then task 8 and 9 have to be done in sequence. So that leaves idle time for the last day and a half with the other two processors. Okay. Now with 3 processors, the job still took 4.5 days. It is a little harder to tell whether this schedule is optimal. However, it might be helpful to notice that since task 1, 2, 6, and 9 have to be completed sequentially, there is no way that this job could be completed in less than what? 2 plus a half plus a half plus 1. Okay, so 4 days, regardless of the number of processors. 4 days is, for this diagraph, the absolute minimum time to complete the job, and this is called the critical time. So critical time is the absolute minimum time to complete the job regardless of the number of processors working on the task. Critical time can be determined by looking at the longest sequence of tasks in the diagraph, called what we call the critical path. Okay? And we're going to stop there. That's the end of this section.